Welcome back to my channel. Today's topic is about alternative fuel at the cement plant. In this video, we will discuss the alternative fuels used in cement plants, their impact on kiln performance, and maximizing the alternate fuels in kiln operations. Both renewable and non-renewable fuels are available. For example, fossil fuels such as coal, gas, and oil are non-renewable, whereas alternative fuels like biomass, industrial waste, RDF, and others are renewable. Alternate fuels used at cement plants are industrial waste, such as bagasse, agricultural waste, such as corn pitch, cotton stick, wheat straw, rice husk, mustard stalk, wood powder, sugar mud, sunflower, grain straw. Biomass such as poultry waste, RDF such as MSW, and TDF includes tires. As non-renewable resources are limited, form over millions of years such as fossil fuels like coal, oil, and gas, and deplete with use, creating long-term sustainability challenges but frequently being more readily available or less expensive now, renewable resources replenish naturally and quickly providing sustainable energy. In short, using alternative fuels to run kilns in cement plants can replace traditional fossil fuels and lead to lower energy costs. The integration of alternative fuels such as biomass, industrial waste, and RDF into cement kilns is revolutionizing the industry. The use of alternative fuels in kiln can lead to up to 40% substitution of traditional fossil fuels, translating to a 10 to 15% reduction in energy costs. However, controlling the combustion process is critical because biomass and RDF often have lower and more variable calorific values compared to coal. For effective implementation, pre-processing the fuels to maintain a consistent calorific value around 15 to 18 megajoules per kilogram, mj/kg, is key to ensuring steady heat input into the kiln. To maintain a stable burning zone temperature is one of the crucial processes, ideally between 1400-1450 degrees C, is necessary to ensure complete combustion of the alternative fuels and proper formation of C3S, a light, in the clinker. A deviation of just 50 degrees Celsius can impact the clinker's burnability, resulting in higher free lime content. Value should ideally be kept below 1.5%. In plants where RDF and biomass were introduced, adjusting the length of flame and increasing secondary air preheating helped stabilize the burning zone temperature, improving thermal efficiency by almost 8%. In terms of kiln feed chemistry, managing the sulfur and alkali inputs is very important because alternative fuels often contain higher sulfur levels. Maintaining the sulfur ratio below 1.5 is one of crucial parameters to prevent kiln blockages and control clinker composition. Additionally, alternative fuels can affect clinker mineralogy, particularly the C3S, tricalcium silicate, and C2S, decalcium silicate phases, which directly have impact on strength development. Regular monitoring of kiln process parameters, such as specific heat consumption, targeting 700 to 720 kcal/kg clinker, and oxygen levels in the kiln, optimally at 1.5 to 2% of the kiln exit, is critical in optimizing the combustion of alternative fuels. The determination for sustainability in cement production is important to increased use of alternate fuels such as RDF, biomass, and waste-derived fuels. However, maximizing their use involves precise control of kiln operations to avoid compromising clinker quality and throughput. As we have already discussed, alternate fuels typically have lower calorific values, causing fluctuations in the burning zone temperature, which needs to be maintained between 1450 to 1480 degrees Celsius to ensure proper clinker formation and prevent excess free lime that could reduce clinker reactivity. Key kiln parameters, including oxygen content at kiln inlet and CO levels, must be monitored to avoid incomplete combustion. When alternate fuels are introduced, following factors needs to done. 1. ID fan speeds often need to be increased by a certain level, 10 to 15%, to ensure adequate draft control and maintain the desired oxygen levels. 2. Kiln exit gas temperature should be kept between 1050 to 1100 degrees Celsius, and stack temperature within 200 to 220 degrees Celsius, so as to prevent thermal inefficiencies and emissions issues. 3. Efficiency of cooler must be ensured above 70% ensures for proper clinker cooling and preventing of unnecessary thermal loss. 4. Adjustments to the raw mix composition are also vital, with a silica modulus of 2.3 to 2.5 and alumina modulus of 1.3 to 1.7 being ideal to stabilize the formation of the clinker while avoiding operational issues like agglomeration. A key factor in achieving these objectives is the plant personnel's in-depth knowledge of the equipment, technology, plant capability, and raw mix characteristics. In short, knowing your kiln, cooler, and combustion systems is key to optimizing operations, maximizing the use of alternate fuels.